Every challenge question, part 43. This is the last chapter of Core Pure 1. It's the review chapter 2. This is a very simple question. We did something incredibly similar in the challenge questions for the transformations chapter. Just going to take x, y, z. We're going to times it by the matrix that reflects in plane x equals 0, which is this. The book just gives you that. Rotation 270. This is rotation 270 about the y-axis. So cos 270 is 0. Sine 270 is -1. So you end up with a 0, a -1, a +1, and a 0. And then reflection in the plane y equals 0 is just this one with the minus put there instead. So it's just this. Expand out those two. All the zeros make this super easy to expand. Like it's just this and this. There's no common non-zero thing, and then there isn't here either. And then there isn't even here either. Sorry, there is at the top start there, right, with the 1 and the -1 to make -1. And then you just keep going, you get this, and then you do the same thing with these two. Eventually you end up with this matrix here. Again, there's very little that, like, this one and this one make nothing. This one and this one make nothing. This one and this one do make a -1 at the end, so that's where that comes from. And then you get the other two rows done, and you're pretty much there, and that's the answer there. Next question, we were asked a very similar thing in the end of the vectors challenge question sections. I'm going to do this differently just because there was a hint on the side of this that I couldn't help but see, which said, consider the angle ABC. So that's what I'm going to do, just because otherwise I would just be copying and pasting the entire slides, which I could do, and I could do it in the same way, but more interesting maybe to do it in a different way. Now, b to a is this vector here. You go down 1 in the x, you go down 2 in the y, and you go down 3 in the z. And then I've said b to c is add 2, -2. And there, to consider the angle ABC, I'm going to do the dot product of b to a to b to c with the modulus of them, and that's going to be cos theta. Now, the modulus of them is, of course, just this. The negatives don't matter when you're squaring them, so that's fine. The dot product is -2 plus -4, which is -6, plus 6, which is 0, which is excellent because that makes theta immediately 90, which is great. These two things are perpendicular. And what that means is if you've got the points A, B, and C like this, the angle ABC is 90, which means AC is the diameter of the circle, which makes this whole thing significantly easy from here, I think, because all I need to do is to work out the center, is therefore work out the midpoint of AC. So what's the middle between -2 and 1? Well, that would be -1/2. Middle of -3 and 1 is -1, and the middle of 0 and 1 is 1/2. So that's the center, easily got. And then to get the radius, I'm just going to work out the distance from here to, say, A or to C. It doesn't matter. So that's going to be a 1.5 squared plus 2 squared from here to here, plus 1/2 squared from there to there. And you just type that in, and you get radius of √6.5, which is the whole answer. So that's nice and easy as well. So that was a helpful hint on the side. You could have done it the same way I did before. Anyway, so this I guess is the hint for this question. It points to it and says chapter 8. So we're intending to do an induction proof to do this. So that's kind of cool. If you have one line, so we're going to start with the case n is 1. This breaks it up into two regions, clearly. And therefore this holds because 2 times 1 is less than or equal to 2, which is less than or equal to, if you put 1s in there, you get 2. So cool. Regions are definitely 2. This rule on both sides holds if n is 1. Now, what you can do is you consider, you can, of course, it's induction, right? So you assume it's true for n equals k. So you assume this is true for some, I don't know why I got that wrong the first time, for some regions if there are k lines. This is just saying the number of regions for k lines is between 2k and 1/2 k squared plus k plus 2. So okay, we've got a bunch of lines here. I've just done 3 to start with. When we add the now I need to go over the kind of the case that creates the least number of regions, and then the case that creates the most number, and then I don't care about the cases that create numbers in between because they're just in between. So the case that creates the least regions is when all the lines meet at a single point. And when you do this and you draw in another line, all that line does is split 2 regions into 2, therefore adding 2 regions. So an extra line adds 2 extra regions, and that will happen every single time. Right? Put a line through here, breaking 2 regions into 2, you're adding 2 regions. So that's why you've got this lower bound here, where the regions is just 2 times the number of lines. Because if every line is meeting at a single point, each line is just creating 2 extra regions over and over again. And so therefore the lower bound is nice and simple, it's straightforward. Add another k, and you just add 2 to these, which can then factorize, I guess, to 2k plus 1, and we can formally say that that's definitely true. And so okay, lower bound is fine. Now the upper bound is the exact opposite case of this, which is when none of the lines meet at the same point. So you've got this kind of idea where any intersection has maximal 2 lines at it. Now, this is a bit more complicated. When you add the k plus 1th line, one way to think about that is the k plus 1th line goes through k plus 1 regions during its existence. And the way to maybe realize that is that it must definitely go through k lines, because there are k lines that it must go through. Like originally here, there are k lines, and it's only allowed to intersect each one once, of course, and it must intersect them all separately because of this rule where they're all intersecting separately. So it intersects k lines, but there are k plus 1 regions either side, right? Because there's sort of k minus 1 regions in between, and then there's 2 regions furthest left and furthest right. If you imagine it as like a road with a bunch of stop signs, and there are k stop signs, there are 2 regions right at the start and right at the end, and then there are k minus regions between all the k stops. So therefore, there are k plus 1 regions in between. But of course, if this line cuts through k plus 1 regions, it cuts them all in half, just like this one did, which means that you're therefore creating k plus 1 regions. Because you're cutting k plus 1 regions, you're cutting them all in half, therefore creating k plus 1 regions as you go through. So, and we've assumed that this is the assumption step, so we've assumed that this algebra here is true. All we're going to need to do to get from our regions made by k lines to regions made by k plus 1 is to say, well, rk plus 1 is just rk plus how many regions are made by the k plus 1 line. But we already have this, right? Rk is just this by the assumption step, and the new regions made by the k plus 1th line is just k plus 1. So we just add that in to the assumption, and then just some algebra here. I just brought these things together, factorized out the half, and then you can sort of weirdly complete the square on this to make it k plus 1 all squared, which leaves behind 2k's left over. Sorry, just 1k left over, because of course it's 2k coming from there. But of course, and then you get a plus 1, which means there's 3 left over, which I've written as 1 plus 2. And of course, the reason I've done that is because now, if you just read rk plus 1 is a half into k plus 1 squared plus k plus 1 plus 2, which is the same as this, just with k plus 1s. And so therefore, by induction, this is proved. You can write the usual spiel, but I think this is done.